welcome. Thanks for coming to our first CSE Atmospheric Sciences Joint Search. Today we have Emily Gordon. She's a postdoctoral fellow at Stanford, working with Noah Diffenbaugh. She's originally from New Zealand, but did her PhD at Colorado State University. And her research is leveraging uncertainty quantification and interpretable machine learning for understanding and predicting weather variability and climate variability. She has won outstanding presentation awards from both the American Geophysical Union and the American Meteorological Society. So I'm really looking forward to her talk, and please take it away. Oh, and one last thing, clarifying questions are welcome, but otherwise keep your questions till the end.
Great, thank you. Yeah, I'm really excited to be presenting for you all today. Some of my work where I've been looking at machine learning approaches and for identifying and understanding predictability on sort of multi-year timescales in the climate system, and really sort of understanding where our machine learning models are making these predictions and what this can tell us about the Earth system. So I'm going to start with let's get rid of that, an introduction to predictability. So let's think about a system where we're flipping a coin. So we want to know, so what are the odds of getting heads or tails? So you can, flip the coin many times and count how many times you get heads and how many times you get tails. And then you should find that you have around a 50-50 chance of getting either heads or tails. So you might conclude that there's no predictability for the system because you can't do better than the sort of random chance that you would expect from the coin flip. However, you might think, okay, what if I now started observing my system? What if I, add a slow motion camera, a speed gun, a barometer, an anemometer? What if, we take this metaphor to the absolute limit and we replace the hand that's flipping the coin with like a pinball launcher, and so we know exactly how much force we're putting on, and we flip our coin again, and then we sort of crunch our numbers. And we find that for some combinations of initial conditions, so for example, if tails is facing up when we start, if we pull our pinball launcher back an exact 1 centimetre, we might find that there's a higher likelihood of tails. So we found that our system does have predictability based on the initial conditions. So now I'm going to go through a climate example of this. So, I'm wanting to go hiking tomorrow in Fiordland in New Zealand. So I Googled it, and it rains, every, 2 out of 3 days in Fiordland. So you might naively think, oh, there's like, a 66% chance of it raining for my hiking trip tomorrow. However, I looked at my weather app, and it says actually there's a 10% chance of it raining for my hiking trip in Fiordland. So what's going on there? Well, we have the initial conditions in the system actually allow us to know that there's a 10% chance of rain. So that the evolution of the system, only 10% of cases will it be raining tomorrow. Okay, but what about I look in my weather app for my hiking trip in 2 months' time? So now my weather app now says that there's a 67% chance of rain for my hiking trip. And this is because at this lead time, there is no skill from our initial conditions. So the memory of the initial conditions in the system is lost. And I've included a little bit a note about if your weather app is providing daily weather forecasts in 2 months' time, you probably shouldn't be using this weather app because they really can't do much better than climatology anyway. So now I'm going to formalize this in a schematic. So along the x-axis here, we have time from the initialization of some forecast to our prediction time. And on the y-axis is our variable of interest. This could be, temperature or precipitation. And in this example here, we have our initial state, and when we look at our forecast, the possible range, so the prediction range, is indistinguishable from this full range, the possible range, what we'll call climatology. However, we might find for a different initial state, maybe a slightly lower anomaly, that by the time we make our prediction, the prediction range is constrained by the initial conditions. So we have a smaller outcome range than the full possible range. So this initial condition provides us some predictability of the system. So where does predictability of this kind come from? So I'm going to make a statement that it comes from a phenomena that have some kind of memory or periodic behavior. And this is a figure from a study that sort of looked at predictability across timescales. And on the x-axis, we're looking at the timescale from weather, so the very short timescales, out to sort of century timescales. And then we're sort of going up and listing all our sources of predictability from the initial condition problem, so making sure we get our initial conditions correct, to the boundary value problem, where it's really important that we're getting the forcings in the system. And I'm really interested on this timescale here, this sort of interannual to decadal timescale, where we're pushing the limit of our initial condition predictability. And so, in particular, I'm interested in these two acronyms here, PDV and AMV. These stand for Pacific Decadal Variability and Atlantic Multi-Decadal Variability. So these are forms of large-scale, low-frequency oceanic variability. And I've included two figures of their corresponding characteristic patterns. And the real takeaway here is that these are sort of large, they span the entire meridional extent of the ocean, patterns that describe where heat is stored in the ocean. And they sort of propagate on these decadal to multi-decadal timescales. So Atlantic multi-decadal variability or oscillation, depending on who you are, where you come from, you might choose AMV, AMO. But this describes sea surface temperature variability or SST variability in the North Atlantic Ocean. And it's unclear if this is actually fully due to internal variability or some of the variability may arise from changes in anthropogenic forcing over the 20th century. No matter sort of where you fall on this, it is, I think, fairly clear that there has been some kind of decadal variability in the Atlantic Ocean. This is shown in this time series. Here is this, the index of this variability. And so it's thought to be sort of a combination of some North Atlantic oscillation, so NAO, plus some Gulf Stream variability, plus some AMOC, so ocean overturning circulation, plus a bit of anthropogenic climate change. When and where each of these matter is still up for debate. I'm also interested in the Pacific Decadal Oscillation, or Pacific Decadal Variability, PDO, PDV. And this is calculated as the first EOF, so first empirical orthogonal function of North Pacific sea surface temperatures. Like AMV, it's thought to be a manifestation of a combination of atmospheric processes, and again, it indicates the heat storage in the Pacific Ocean. Once again, along the, this panel here shows the timescale of the time series of the Pacific Decadal Oscillation in the 20th century. So interesting with the PDO is it's associated with temperature and precipitation variability over North America. So if it's in a certain state, the precipitation might be a little bit anomalously high over, for example, the West Coast. It also affects marine ecosystems. So interestingly, the PDO was discovered by people, I think at UW, actually looking at fish, fish populations. And this pattern is so large that it's likely contributed to sort of modulations in the rate of global warming. So it's thought to have contributed to sort of a speed up of global warming around the 1980s, and then also the hiatus period around the early 2000s. So I'm calling this a non-exhaustive list of interesting questions because there are so many interesting questions in the world, but these are the ones that I'm interested in. Can we predict low-frequency modes of variability and increase our understanding of these processes? Can we identify states of enhanced predictability? So this is going back to before, these states that are more likely to have predictable outcomes and their contributing mechanisms. And lastly, what does predictability look like in a future climate that's dominated by anthropogenic greenhouse gas warming? And I'm going to use machine learning for my work. And I'm not going to go through all these studies here, but these are some really lovely machine learning papers in climate and atmospheric science, which have shown that we've been able to make some really good insights in recent years using these new tools into our climate system. So I'm going to use, in this first study, an artificial neural network, and I'm going to go through briefly how this works. So we're going to take some input information. So here it's going to be maps of ocean heat content, and we're going to connect them to our neural network, which is a network of nonlinear functions. So we can consider each of these points on these maps here as being connected to each of these nodes. Each connection represents a weight, and then when we get to each of these nodes, we add a bias term, and then surround that whole thing with an activation function, which sort of governs if or how much information is passed forward into the next layer. So you can see we have this layer of nodes where we're sort of deciding how much information to pass forward, and then we can add another layer, weight on all of these, another bias, more activation function. So we can build up these sort of nests of network, I guess would be the word, of nonlinear functions. So this is a neural network. And then our output will be a prediction of something which should probably be related to the input. So I'm going to go through an example of using ANNs to predict the PDO. So like that previous example, I'm going to input maps of ocean heat content lagged by 4-month intervals into a very, very simple artificial neural network. And then our prediction problem is going to be asking this neural network, will the PDO change phase? So will it switch sign in the next 30-month period? So, if this is our input period, these 3 black dots, what's going to happen within this pink window here? So an example could be, following this dotted line, we cross through 0 here, so we do change sign, so a correct prediction here would be transition. For this study, I used 2,000 years of climate model data from the Community Earth System Model version 2, so CESM2. This is a fully coupled climate model with ocean, atmosphere, land, and ice. It's a pre-industrial control run, so there's no anthropogenic greenhouse gas emissions. And the reason we use this is it allows us to examine internal variability without the influence of climate change. So I call this rainbow world because humans aren't there to mess everything up. So I'm going to go through some sort of basic results. So first of all, I'm looking at predicting persistence in the PDO. So this is saying the sign of the PDO does not change. So we're looking at persistence of the positive phase. So this is a composite of the correct input maps for a positive to positive persistence. And this is a composite 30 months later. Not super interesting, the PDO didn't change because, that predicted that it wouldn't change sign. So it appears that the ANN is learning persistence in the PDO, but can we be more sure about why our neural network has made its decisions? So I'm going to use an explainability technique, an explainable AI technique called layer-wise relevance propagation, or LRP. So for a specific prediction, we can use LRP to generate a heat map which will indicate points on the input map that are relevant to a network's prediction. So for example, we could take this picture of Rosa the dog, input it into an online image classifier, which gives us a prediction of dog. So good job, online, you did it. And then apply LRP to our prediction to get a heat map of the points that were relevant to the prediction. So you can see here for Rosa, they've indicated her eyebrows and her ears, a little bit of her tail, and also her dog tags. They've noticed that dog tag means dog. So, in the context of this problem that I was looking at before, this is our composite of inputs. So this is our persistence inputs. And then this is the composite of the corresponding LRP heat maps. And so we see that, yes, the neural network has noticed that this sort of characteristic horseshoe pattern in the North Pacific Ocean is indicative of persistence in the PDO. So this is, suggesting that our ANN is making the right prediction for the right reasons. But, let's look at something that may be a little more interesting, and that's these transitions in the, hello? I'm inputting three ocean heat content maps. Here I'm just showing the final input map. Yeah, cool. So now we're going to examine transitions in the PDO. So here is our OHC at that final input map, the composite for positive to negative transitions. And I've contoured over top in the solid contours the positive relevance regions for making a transition prediction. And here's the corresponding LRP heat map. And so we find that heat content in the Western Equatorial Pacific is important for making our PDO transition predictions. But in the PDO regions, in the ENSO regions, or in the tropical Pacific, it's actually not particularly useful. So why might that be? So there is a PDO transition mechanism that has been posited in the literature, which sort of posits that we have this buildup of heat content in the Western off-equatorial Pacific, which we're followed by an ENSO event, so in this case a La Nina, so we have these negative anomalies in the tropical Pacific, can force a PDO transition. So this is sort of the following through from this input map that I had. When I look at when transition occurs, we do find these a strong La Nina event, and then 30 months later, indeed, the PDO has changed sign. So this is indicating that the neural networks were able to sort of learn these preconditioning for a PDO transition. So then we look at negative to positive transitions, which actually behave a little bit differently. So again, we have this relevance in the off-equatorial Western tropical Pacific, but we also have a really strong anomaly here in the Atlantic Ocean. And so I said before that to cause a PDO transition, we need an ENSO event. In the previous case, it was a La Nina event, but in this case, we need an El Nino event to transition from a negative to positive PDO. And El Nino events are thought to be a little harder to predict than La Nina events. La Nina events often follow from an El Nino, but El Niños sort of need a bit more ocean preconditioning. And one of the things that's positive to sort of be a precursor of an El Nino event is this negative anomaly in the Atlantic Ocean here. So it appears that the neural network has learned a sort of extra information it needs for this opposite sign transition. So once again, we can go through the similar story, looking at our OHC in the final input month. When the transition occurs, indeed, we do have an El Nino event, and then 30 months later, we have our PDO transition. So just quickly going through the results of this first part, we find that our artificial neural networks can predict low frequency modes of variability. So we've learned about the PDO in CESM2. We can use XAI to investigate precursors of predictability. So these transitions seem to be preceded by a heat content buildup in the off-equatorial Western Pacific. And then also that the ANNs can recognize the asymmetry and predictability, or this sort of non-linearity between El Nino and La Nina events. And this paper is available in GRL. Okay, so I'm going to return now to the schematic that I showed earlier about sort of the difference between a prediction that is constrained by initial conditions and a prediction that isn't. So we find that some initial states have more skillful outcomes than others. So we have found that this is true on multi-year timescales. This figure is from a paper which looked at the skill of predicting sea surface temperatures in the North Atlantic subpolar gyre. And this red line here is for the skill of forecasts that were initialized during periods of anomalously strong ocean heat transport into the gyre. And the blue is for anomalously weak transport into the gyre. And this is showing anomaly correlation coefficient, so the skill of these forecasts. And we see that this red line is higher than the blue line, so there do appear to be periods where these forecasts are more skillful. And this is a state of sort of more predictability for North Atlantic sea surface temperatures. Similarly, a study used the CESM decadal prediction large ensemble and found that the information retained in a hindcast, so the sort of information within the forecast is higher for forecasts that begin during a sort of anomalously high state of AMO, so basically a lot of heat in the North Atlantic Ocean. So this is building on this idea that, like, wouldn't it be really nice to know a priori if our sort of climate level forecast is going to be good? So I'm going to investigate this thing called state-dependent predictability, so how prediction skill varies with initial state. So I'm sort of giving a name now for this concept that I've been sort of going over. And in particular, we're going to look at identifying windows of opportunity for enhanced prediction skill, or the initial states that are most likely to be skillful. And it's been demonstrated that neural networks are great for this. In particular, this is previously done in classification tasks. So here we have a study that looked at the predictability of subseasonal circulation predictions, and they used the neural network's confidence output to find the most predictable states for North Atlantic circulation. So I'm going to look at training a neural network to predict sea surface temperature anomalies at this point in the North Atlantic Ocean in 1 to 5 years. And a similar neural network set up to before, inputting information about ocean heat content, this time at different levels in the ocean. So if we sort of naively set this up as a neural network regression task, so we're asking our neural network to predict a future anomaly, we'd get something like this. So, with our truth along the x-axis and the predicted along the y-axis, this is not a great fit, really. You would, some of these dots, so I've indicated with pink arrows, are better than other predictions with the green arrows. So we want to somehow know if our prediction is going to be closer to this one-to-one line, or our prediction is going to be closer to the truth. So instead of just predicting a sea surface temperature anomaly, we're also going to get our neural network to give us an uncertainty estimate with its prediction. And our neural network is trained so that it's not penalized for predicting a high error anomaly as long as it guesses a correspondingly high uncertainty. And so what this means is that if we grab our predictions with relatively lower uncertainties, is that their predicted anomalies should be closer to the truth. So I've indicated this here, that once we add these uncertainty bounds, we can sort of see, we can see the uncertainty bounds. And a note on the nomenclature that I'm going to use. So when I use mu, I'm going to refer to the predicted anomaly, and sigma to refer to the predicted uncertainty. Once again, I'm using my 2,000 years of climate model data because we're wanting to examine internal variability without the influence of climate change. So we're predicting sea surface temperatures in the North Atlantic subpolar gyre. And so this is our map of truth versus predicted. Once again, not the best, but can we find these states of enhanced predictability? So one way I'm going to do this is using this thing called the discard test, which is, as it says on the tin, it's discarding samples with increasingly lower uncertainty values. So for example, if we look here at the 100% most confidence, so this is keeping all of our testing data. So this is just the skill across the entire testing set, and our mean absolute error is 0.52. This is standardized error. However, if we only keep 20% of our samples and we choose the 20% of samples that have the lowest predicted uncertainties, we find that our error has now dropped to about 0.42. So this is demonstrating that our neural network is able to identify predictability within the data by assigning it a relatively higher or lower uncertainty. So I trained a neural network at each point in the ocean. So this is, pointing to this point up here. And then if we do the same thing at each grid point, we look at the 20% most confident predictions. This is this map here on the right. And we're looking at mean absolute error, so brighter is better. And then we subtract the two to find places where the 20% most confident samples have better skill, so the places where we are identifying these states with enhanced predictability. So that's all of these red regions here. So this is indicating that even in the mean, we might not have that much predictability, but when we start to really probe these states of enhanced predictability, it really exists sort of widespread across the ocean. In particular, sort of North Atlantic, North Pacific, and across some of the Southern Ocean. Okay, so once again, we want to think, okay, what are the actual mechanisms that are providing us predictability on these timescales? So I'm going to look again at our point in the North Atlantic Ocean and look at the samples, the predictable samples identified by the ANN's uncertainty output. So we grab the 20% most confident samples here, and it just so happens that these are mostly predictions of positive anomaly at this region here. And this is using, so this is a composite of these 20% most confident samples. And then down here we're using 3 different XAI or XAI methods for understanding where the, for understanding which grid points were relevant to our neural network's predictions. So we find that they sort of overwhelmingly point to this ocean heat content anomaly in the subtropical Atlantic Ocean. And if we look at the sea surface temperature over this period as well, we find that we have a corresponding sea surface temperature anomaly, 1 to 5 years before our prediction, which has moved into the subpolar gyre 1 to 5 years later, suggesting that it is one of these states of enhanced predictability when we have a period of enhanced northward heat transport. Something else that was interesting to me here is to look at sort of what's going on sort of basin-wide here. So we look at the AMV index, so sort of an index of Atlantic variability. The shading here indicates the full range of variability within the data, and the solid line is just for these samples in particular. And we find we have a slightly positive AMV index when we have a skillful prediction, which is, I think, slightly unsurprising. But if we look in the Pacific Ocean, so here I'm using something called the IPO index. It's very similar to Pacific decadal variability, but it includes the full meridional extent of the Pacific Ocean. So once again, we have our shading is the full testing data, but our 20% most confident samples are this outline here. And so we find that when our ocean is preconditioned for this predictable state in the North Atlantic Ocean, we have a really strong negative IPO signal here. And this is really, really interesting to me, this idea of, if our explainability method is highlighting this region here in the North Atlantic Ocean, what else is happening in the ocean that may be helping to build these predictable initial states? So to summarize this section, I've looked at artificial neural networks predicting sea surface temperatures on decadal timescales. It beats persistence for 2 different lead times, which I have in the supplemental. Neural networks identify these more predictable states by assigning lower error to lower uncertainty to predictions that are more likely to have lower error. And we can use these predictable initial states to sort of probe the predictability, the mechanisms leading to predictability. And I have shown an example in the North Atlantic Ocean. And once again, this study is also available in geophysical research letters. Okay, so I'm sure we're all thinking, oh my goodness, this is great. We can make predictions of our future variability using our initial condition information, right? We're living in this rainbow world. No, we're not. We're living in a world where humans have had, quite an influence on our climate in the last, 100, 150 years or however long. So I sort of skipped over this a little bit earlier, where I said that Earth system phenomena, predictability comes from Earth system phenomena that have some kind of memory or periodic behavior, because predictability also comes from the human impact on the climate system. So here, now we've added this little GMST here, which stands for global mean surface temperature. So the predictability on decadal timescales can be provided by the expected increase in global temperatures in the next few years, also from the external forcing in the system. So I'm going to go through an example of what we mean by predictability from external forcing. So this is a figure here which is showing global mean surface temperature. So the red is land only, the white is global, and the blue is ocean only. And these are all showing a rise in temperature over the last sort of 50 years or so. Now, this is like a thought experiment because I don't have $1 million, but I will give you $1 million. If you can predict whether surface temperatures in 2030 relative to right now, let's say in the Washington region, will be higher than they are now, lower than they are now, or about the same. Now, you're going to say higher because you want to win $1 million. But actually, when we look on more regional scales in the climate system, there's a much more variability than we actually, than just, temperatures will continue to rise. So here I'm showing a time series of sea surface temperatures from this box here in the North Pacific Ocean from the CESM2 large ensemble. So this is a climate model version of the historical period and also the next sort of 80 years up to 2100. And the blue line is one version of how the climate might actually behave, and the black line is an estimate of the approximate forcing from humans. So I'm highlighting this region here from 2020 to 2060, and I've drawn on 4 sort of consecutive decadal or 10-year trends. And what we can see is even within the next 40-year period, we have periods of, anomalously high warming or increased sea surface temperature trend. But we can have these periods of cooling as well. So, and a question that I'm really interested in, would something like this be predictable in the presence of this background forcing trend? So we're going to take a machine learning approach to this. So I'm going to sort of give an example of how our prediction system is working. So we're going to go over an input period of about 15 years and input our neural network information about the forced response to climate change and information about the internal variability of the climate. And our output will be a prediction in the next 10-year period, will the future 10-year trend lie in the lower, middle, or upper third of the possible sea surface trend distribution? And the way we're going to do this is we're actually going to split this into 2 parts so we can really break this down into the contributing parts of the system. So we're going to connect the forcing to one neural network and the internal variability to another neural network. And each of these networks outputs its own tercile predictions. These predictions are then summed in the final step, and the prediction with the highest sum is considered the winning prediction. And these are trained at the same time, so the neural networks must sort of learn to work together to weight their contributions to the final outcome. So I'm going to go through just an example prediction. This is a real prediction from the neural network trained at 20 to 30 south and 60 to 70 west, making a prediction of model year 2033 to 2042 in ensemble member number 9. So this is real, typing it into my computer and telling me to output all these numbers. So the external forcing network predicts about 0.1261 here, so it's predicting a upper tercile trend. But the internal variability network is putting a lot of weight on this lower tercile trend. And then when we combine the predictions together, we find that it is the lower tercile trend that is the winning prediction. So this demonstrates that even in this sort of period, in the next sort of 40 years, there are periods where we can make predictions of a negative trend from internal variability information. So internal variability is contributing to the predictability of the system. Oh, I just said all that. Okay, so once again, I have trained these neural networks at every point in the ocean. And here I am showing the skill of the neural networks, so just sort of as a quick check to make sure that we're getting more skill in places we expect. So once again, we have skill in the North Pacific, skill in the North Atlantic, and then skill in the Southern Ocean. So we can sort of check the box, yes, these neural networks are making sensible predictions. So now we want to tease out the contribution of internal variability to our predictability. So this is the figure I just showed. And now we're going to do something called permutation importance testing to examine the contribution of internal variability. So we're going to keep our information about external forcing the same, but we're going to scramble the information about the internal variability. So an example prediction task could be inputting the external forcing map from 2020 to 2030, and then inputting garbage, but correctly distributed garbage, into the internal variability network and asking the full network to still predict 2030 to 2040. And then we recalculate our accuracy at each grid point on this shuffled internal variability data. So this is, as before, our accuracy across all data, our accuracy with our shuffled internal variability data. And then this figure here is just the difference between the two. And so an interpretation of this figure was if the networks were only using external forcing to make their predictions, this figure would be zeros everywhere because internal variability would not contribute to the neural network skill. But we do find skill in the North Pacific Ocean and in the North Atlantic Ocean. So this is suggesting that the internal variability does significantly increase the neural network's accuracy above external forcing. So another question might be, so what is the governing variability leading to predictability in all of these regions? So what I did is k-means clustering the predictions at each grid point where internal variability was important to predictability to look for regions, group together regions which had similar precursors of predictability. So we found that we had a cluster fallout that resembled the PDO horseshoe, and examining the variability at these points showed that this predictability was derived from the timescale of the PDO. We find a cluster that resembles, which is in the tropical Pacific or in the ENSO region, and this appears to be predictability from sort of an aliasing of an interannual El Nino variability. And then we also find predictability in the North Atlantic subpolar gyre. Once again, this is the timescale of ocean heat transport into the gyre. But we also have these sort of remote clusters falling out. So we have this sort of one which highlights points around Australia, New Zealand, and sort of off the coast of Europe. We have this sort of South Pacific and coastal Indian Ocean cluster. And we have also a subtropical Atlantic, subtropical North Pacific, subtropical cluster. So this is another interesting question to me. Once again, we've had this sort of remote regions which are co-varying at the same time when we have predictable signals. So what is leading to this covariance in predictability? So summarizing this section, we've designed this interpretable neural network to decipher contributions from competing mechanisms in the Earth system to examine sort of attribution to predictability problems. So in this case, looking at internal variability and external forcing. We find that internal variability contributes to predictability even in a moderate to high forcing scenario. So in this case, it was the northern mid-latitude oceans and the tropical Pacific that were important. And cluster analysis has revealed the regions with covariant predictability. And the study is in environmental research letters. So I have sort of a few concluding thoughts and future directions of this research. So this work was all focused on sea surface temperatures. So what can we do with that? So these two studies on the right and in the middle are doing these things called hybrid dynamical statistical models. And what we do is they're taking skillful predictions of ocean variability and looking at what we can say about the land surface when we have oceanic predictability. So on the left, they make a forecast, use a dynamical model to make a forecast of ocean variability in the North Atlantic and connect it to precipitation predictions over Portugal and find that they have skill in 2 to 9 years' time. And similarly, the study looks at sea surface temperature predictable using a dynamical model in the North Atlantic Ocean, but this time predicting surface temperatures over Europe. So this is using ocean prediction to constrain the variability over land. And I'm showing this figure here, which shows the sort of correlation relationship between PDO and ENSO and wintertime North America precip and temperature. So this is me suggesting that, if we can understand how the PDO or North Pacific will vary in the next sort of 5 to 10 years, then maybe we can make, a constrained statement about the amount of precip or the sort of temperature variability we might expect in the wintertime. Another thing which I've suggested a few times is this idea of covariant predictability. So if we have predictability in one part of the ocean, what's happening elsewhere? Is this also sort of communicated elsewhere? So in this cluster analysis, I suggested some of these remote clusters. And then I also suggested in the CESM pre-industrial control, when we were looking at North Atlantic variability, we found a negative IPO signal. I had a great REU student a couple of years ago who looked at this similar pattern in the MPI model, so the Max Planck Institute model, and he found the same thing, that when we have this sort of state of enhanced predictability in the North Atlantic Ocean, we also have negative PDO-like variability in the Pacific. So this is, a really interesting question to me, because, if we know that that we're in a predictable state somewhere, what does that say about what's going on in other basins? And this is a figure I showed early on, but I really wanted to come back to it and say that thoughtful applications of machine learning can provide new insights about our climate system. So really thinking about how we set up our problems, what are the methods that we can use, and we can really get some great new insights into what's going on in my case, sort of these sort of multi-year timescales. But this is, I guess, finishing with kind of like a sort of a warning for the future. If we are going to be using these ML-based decadal predictions, or we're looking at making these multi-year predictions, what do we need to do as scientists? What sort of research should we be doing before this is used in decision making? So this is this study on the top left is a prototype for providing a decadal climate service, where we're working together with scientists and users to figure out what's the best way to provide usable information. The study on the top right came from this decadal climate service, looking at making predictions of future Atlantic hurricane activity, and then the associated forecast US hurricane damages in the next 5 years' time. And these used initialized hindcast models. The bottom left is getting at these hybrid approaches that I was talking about before, so combining a dynamical model with a data-driven, maybe a machine learning model, to think about how we can sort of use information from both to make our predictions. And then finally, this figure has looked at evaluating explainable AI methods when used in Earth system problems, to evaluate what they're actually telling us about the inputs, what these sort of saliency maps are telling us about our inputs, and are we actually interpreting them correctly? So I just wanted here to acknowledge some of my collaborators. So my advisors, Noah Diffenbaugh and Libby Barnes, and then Jim Hurrell and Francis Davenport, who I worked with at CSU, and then Abe Tico, who was just an incredible REU student that I had a couple of years ago at CSU. Please, reach out to me if you have any questions. I have all of my code is available on GitHub as well. So thank you, and I'll take any questions.
Yes, so thank you for a very interesting talk. I'm a total non-expert, so I don't know about atmospheric science, but I'm imagining there must be some physical models that can do the same prediction based maybe on partial differential equations, nonlinear ones. So I'm familiar with the critique that people have done for the large language models and for deep neural nets. They have pros and cons. So my question is, what makes you think that ANN could compete or outperform or replace physical models that are out there?
So I think one of the powers of this technique is so in the second study, when we were looking at the uncertainty quantification, is that was a very cheap way to get uncertainty values. So the sort of other standard way of making these timescale climate predictions is, as you suggested, running a dynamical model. But to make sort of a comparable data set, you need to run your model for usually around 10 model years, usually with about 20 ensemble members, and you have to do this for each start date. And so it's like a huge computational expense. So we're able to provide insights about the predictability of the climate system with one long control run from a climate model, and also avoid some of the biases that comes from sort of comparing to running these climate models and comparing them to observations.
Thanks for the nice talk, Emily. I had a question on part one. So you were showing some interesting reasons for those PDO transitions, and I was wondering if you had any mechanisms why those particular regions were important. Like, why do they differ between the positive and negative phase transitions, and sort of, is that what we'd expect, or yeah, why are those regions the ones that jump out from the?
Yeah, let me see. Yeah, so the top panel has the superimposed explainability contours. Yeah, so I'm not going to completely describe the mechanism off the top of my head because I will butcher it. But having this heat content anomaly in the western off-equatorial Pacific sort of gives us this heat content here that we're able to sort of, I don't want to say drain, but sort of drain and pull into the equatorial region to force the ENSO event, which then sort of leads to a transition. So it's sort of an interesting, there's a really interesting sort of paper on this where it says the heat content anomaly is a sort of a necessary condition for a PDO transition, but it's not a sufficient condition, is you do need a following ENSO event, but you're not guaranteed to have the following ENSO event of enough size to affect a PDO transition. So what we're really looking for is sort of the most likely inputs that will lead to a PDO transition. So the reason we had a difference between positive to negative phase transitions and negative to positive phase transitions is this ENSO event. It's really sort of relying on this ENSO event to affect the transition. And so when you're going from a positive to a negative phase, you need a La Nina event, and these often follow from an El Nino event, so they're more predictable. So that's why the neural network didn't have to, I think, was only sort of looking for this heat content anomaly, whereas for the negative to positive transition, this Atlantic anomaly here, also off the top of my head, I'm not going to repeat the mechanism because I'll get it wrong, also sort of aids with the preconditioning of the future El Nino event.
Thanks very much for your talk. I had a question about your tercile splitting up of your results. You had the softmax classifier, and it seems like your ensemble number 9 produced results that are pretty close between no transition and the middle case and the cold case. And I just wondered, is this typical? So the cold case was the winner here, but doesn't seem really by all that much. And I wondered, what typically comes out of this? How unequivocal are the results coming out of the classifier?
Yeah, so I think that's getting at yeah. So when we're looking at the most confident samples, those would be a prediction of an upper tercile, because that's when you would have agreement between the internal variability and the forcing in general. So in terms of being confident about lower tercile predictions, that happens a little bit less. One interesting thing that we did find was, I wonder if I have it in my supplementary, is there were cases where, I didn't put it in, bother. The sort of load was split, so the external forcing network predicted an upper tercile, and the internal variability predicted a lower tercile, and they sort of balanced each other out, and the actual winning prediction was that middle tercile coming out from that. So it was sort of showing that the neural networks could sort of learn to cancel each other out almost. But yeah, in terms of confidence, normally the ones you'd be most confident about would be an increasing trend.
Thank you.
Okay, so I'm thinking of some of the problems that climate scientists argue about having to do with decadal variability. One of them is the cause of the AMO and how important anthropogenic aerosols might be. And then the other one is, say, the Pacific variability, and to what extent is it an internal variability that's driving us into a particular phase, and to what extent is it, say, teleconnections with Antarctica, et cetera. Does machine learning help us with any of these questions? I mean, there are lots of interpretability metrics, but I guess I'm wondering, interpretability in the classical science sense of mechanism, how can you make that connection?
Yeah, so in terms of my own research, I can only point to this clustering I did where the variability leading to predictability in the North Pacific was distinct from the variability in the El Nino region, suggesting that that they are different. So, suggesting that it's not just, ENSO driving North Pacific variability. In terms of pulling out the governing modes of variability for, or the governing variability for A and V, I haven't thought a lot about that. I've been thinking mostly, so using these pre-industrial runs so that we sort of don't have to worry about this problem with the forcing. And from this, I sort of take the opinion that there is internally generated variability in the North Atlantic Ocean, but to what extent has it just been sort of swamped out by changes in anthropogenic forcing is a question I don't know the answer to. And I'm interested in thinking about ways that we can use existing data and data-driven methods to tease out those mechanisms.
Yeah, thanks. Yeah, so in your prediction model, is your initial state is at given time or at many times? Because I would guess, in order to predict what's happened next 10 years, if you use all 40 years data before, from satellite, we would expect better predictability. And my question, if so, how sensitive to, the different time of initial dates you use? Thanks.
So in each of my studies, I used slightly different amounts of information. So the first one, I think I had 3 maps with 4-month lead times. And the second one, instead of using different lead times, I looked at different depths of ocean heat content anomaly, but at the same time, because the deeper you go in the ocean, the sort of longer you're looking back in time. And then with this final study, I looked at giving it to the neural network 2 overlapping 10-year periods of sea surface temperatures. In some places, this did improve the neural network skill, and in some places it didn't. So looking in the case of training over all grid points, I think the models that I'm using are relatively simple. So I think I'm almost reaching the amount of skill you can get from a neural network of this complexity. But I like to think that there have been some pretty valuable insights from examining the problem in a very simple way.
I have some questions about how your experimental result sensitivity to your model structure. I mean, for most of your research, you use fully connected network for prediction. So if you change to another like self-station network, how your result improved, and how your signals maybe differs with this fully connected model.
Like I think similar to the previous question, I wanted to keep this as simple as possible, and so using the fully connected artificial neural network as a way of doing this. We found we didn't need to go into convolutional neural networks, so looking at sort of image-based, because using only one climate model, as I did here, you don't expect the sort of where the patterns are to change, so we don't need to scan an image to find the patterns, for example. I'm interested now in moving away from using a single model, using multiple models to learn sort of from each of the models, what can we learn about Earth system predictability? And I think that's when convolutional, I'm using those now because I think you need the ability for the transformation or translation.
early on to find the sort of important regions? As someone that doesn't really know anything about machine learning, I was just curious if you could explain sort of how that worked to get sort of like you showed one image with horseshoe in the North Pacific.
Yeah, so this is called layer-wise relevance layer-wise relevance propagation, or LRP. In this case, it's the same as doing a method called input times gradient, which what you're doing is at each grid point you're testing the sensitivity of sort of a small perturbation of the grid point to the sensitivity of the output to small perturbations in each of the input grid points, and then you multiply it by the input mass, so you get like the sign sort of gets in the right place. So this means that This means that positive perturbations in this region here result in a more positive prediction here. Is sort of the sort of way of thinking about it. Yeah.
Your approach depends on using a GCM that's, we know has flaws, significant flaws, especially in terms of natural variability. So why do you think that you can use this approach to actually get skillful predictions in the real world?
Yeah, I think that's a good question, and I think it's there's a lot of research, not my own, that shows like just surprisingly how good these models are at predicting the real world. One thing I found actually is like training across. I've been training across many different climate models now, and then testing on observations, and we are able to get skill within the observational record of variability. So this is suggesting to me that that I think this is a consequence of something called the signal-to-noise paradox, which is that observations actually have more of a signal of internal climate variability than the climate models do. And so the neural network's actually able to sort of learn enough of the variability that when you test it on observation, it was like, oh my goodness, there's actually more of a signal here to predict.